Alright guys, let's go over number 1 and then we'll move on to number 2. So for number 1, it's asking if you got a constant temperature, the change in volume will not affect which one of these reactions. Now, it doesn't specify if it's it's expanding or it's contracting. It doesn't tell us if the volume goes up or down, and so we don't really need to consider that too much. So if you think about volume, if you change the volume, what else changes in the system? Yeah, pressure. So a change in volume is going to lead to a change in pressure. Okay. Easy way to kind of think about this and remember it is think about the ideal gas law, PV equals nRT. It tells you the temperature is constant, so you don't really need to worry about the temperature. The volume is changing. We know the R doesn't change, right? That's a constant. We are looking for something that doesn't change the moles. And so if you change the volume, that means the only thing that has to change is going to be the pressure. So that's kind of how mathematically you can derive that. But just know, if you change the volume, it's going to change the pressure. So we need to look at these reactions right here where basically shifting it left or right will not change the pressure. Now, the only way to not change the pressure is going to be the reaction with the same moles on both sides. Okay? Right? Because if you have the same number of moles on both sides, whether it shifts left or right, you have the same moles of gas. So the composition of the mixture will change, but the actual pressure will not. So if you guys take a look at this, which option has the same moles on both sides? A. Yeah, you got 2 moles on the left and 2 moles on the right. So good. So that's if I'm being honest with you, it's a pretty simple question. It's just whether or not you know moles of gas is equal to pressure. But again, just know that changing the volume will affect pressure at constant temperature. Okay. All right. Any questions on that one? All right, let's go to number 2. And for this one, I need to give you a little bit of, I guess, preliminary information. And then after that, I think it'll be pretty easy for you guys. So it's asking you to find the equilibrium constant expression for the hydrolysis of this ion right here. Now, hydrolysis is basically where you add a hydrogen to whatever you're trying to hydrolyze by reacting it with water. Okay, so hydrolysis is where you try to add hydrogen to whatever you're trying to hydrolyze by reacting it with H2O. Okay, so you have your ion right here. Okay, and what you're doing is you're reacting it with H2O, and then you're trying to add hydrogen to the ion that you're trying to hydrolyze. Okay, now before I have you guys finish it up, let's go over the state of matter. So let's start with H2O. What's the state of matter of H2O? Yeah, it's going to be a liquid. And if you're reacting this ion with water, what does the state of matter of this guy have to be? So we got options: solid, liquid, gas, and then the last one is aqueous. So this thing is inside of water, right? So what does this have to be? Yeah, this has to be aqueous. Okay. All right, so I will give you guys a couple minutes to finish that up and see if you could find the equilibrium constant expression. Again, just keep in mind you are adding hydrogen to this ion through water. All right, guys. So I finished the equation for you guys. If you're hydrolyzing this ion, you're going to add a hydrogen to it, so it becomes HC2O4, and it's still aqueous, and it got the hydrogen from water. So water gave one of its hydrogens to the ion, and so water becomes it becomes OH minus. So that's going to be your reaction. Any questions on how we get that reaction? Okay. Again, just remember, hydrolysis is where you add hydrogen using water. Okay, so from here we can do the equilibrium constant expression. Pretty simple. The key thing to identify is that you're going to ignore the liquid, right? Because the liquid is not a part of a equilibrium constant expression. And so you just look for the guy that's going to have, what was that? Yes, it's going to be C because it's going to be product. So these two should be on top of the fraction. So you're going to look at the equation that starts with that, and then you're going to get C. All right, any questions on that one? Yeah, what's up? All right, so let's go over number 3. So for number 3, there's one answer that's, I'd say, the one that should glaringly pop out to you as the incorrect answer. And that one will be D. Okay, D is not going to be correct because if you guys think about equilibrium, we don't count solids in the equilibrium constant expression. So it doesn't really matter how much of the solid you add. I know that it says you want to increase the product, so you guys might have thought, hey, I can add some reactant and then shift it right. That's half right. The problem is this guy is not included in the equilibrium constant expression. So D is the one that's kind of there to trick you, but it's not going to be the answer. Okay. Does that make sense? Why though? It's because it's not in the expression. It's a solid. All right, let's go A, B, and C. Let's go in order. So let's think about A. If you decrease the volume of the container, what does that do to the pressure? Yeah, it's going to increase the pressure. Now, if you guys take a look at the reaction, how many moles of gas are on the reactant side? 1 mole. Good. There's just this guy right here. And on the product side, you have 2 moles. All right. So if you decrease the volume, what that means is the pressure is going to increase. Now, if you guys remember the chandelier principle, right? It's going to want to fix that. So if the pressure is increased, the system wants to bring the pressure back down, right? So the system wants to bring the pressure back down. And how can the system bring the pressure down? Which way does it want to shift, left or right? Yeah, it's going to shift left. So if you decrease the volume, it's going to shift to the left side. It's going to increase the reactance. So A is not going to be our answer either. It does the opposite, okay? Okay, so the logic is decreasing the volume will increase the pressure. The system is like, whoa, equilibrium we're not in equilibrium anymore. We got to bring the pressure back down to get close to equilibrium. So the system brings the pressure down, and the way that it does it is it starts making more reactants. Okay, so A is not our answer because the point is to increase the products. Okay, any questions on the logic of that? Okay, I know this part might be the one that's a little bit confusing, but whenever you disturb equilibrium, remember the system does the opposite in order to get back to equilibrium. Okay. All right, let's go to B. B is a little bit confusing because if you look at it, you're messing with 2 variables, right? So let's look at B. I'll do that one in blue. So you're raising the temperature of the container, and you're also increasing the volume of the container. Okay, now before we do that, since we're working with temperature, we need to think about the enthalpy. Okay, the enthalpy is greater than 0. So is this an exo or endothermic? This is going to be endo. And if it is endo, it means heat is going to be a reactant in this reaction. Okay, endo means that heat is a reactant. So far, so good? Okay. So let's go to temperature. If you increase the temperature of the system, okay, what that means is the system, it wants to bring the temperature back down, right? So if you increase the temperature, the system wants to reduce the temperature because of the chandelier principle. It has the opposite effect. Now, in order to decrease the temperature, what the system is going to do is the system is going to shift to the left. Okay, and this is the part where it gets a little bit confusing, so I'm going to draw a little picture to kind of help you guys out. So let's say this is our container and we have our, our system inside of it. We have our gases and then we have our solid carbon. Now, this thing has a equilibrium temperature, right? In order for the temperature to, if you increase the temperature, basically if you make this thing hotter, what's going to happen is the system wants to bring the temperature back down. And the way that it brings the temperature back down is it starts using the heat in order to, it uses the heat in order to make more reactant. It starts to shift to the left side because heat is used to go to the left side. And so that's why if you increase temperature, system does the chandelier principle and it shifts the system to the left. Okay, because if heat is released on this side, that means that it's going to shift it to the right. Okay. All right, and then for the volume, if you increase the volume, what does that do to your pressure? Yeah, it's going to decrease the pressure, right? Bigger container, lower pressure. And so if you decrease the pressure, the system, it wants to increase the pressure. And the way that it does that is it's going to shift the system equilibrium to the right. So you have two disturbances that are working in opposite ways, right? But you don't know which one is greater. So we'll put a pin on that. That's maybe an answer, but we don't know if the shifting, which side the magnitude is greater for the shifting. Okay? Any question on that? That's kind of the tricky one to analyze. You guys good? A little too early for this? Okay. All right, and then the last one, part C, lowering the temperature of the container. So if you decrease the temperature, that means that the system, chandelier principle, is going to want to increase the temperature. And how does it increase the temperature? Well, it wants to do that by releasing energy. It wants to release energy. And the way that it releases energy is by shifting it to the right. Okay, and so your answer, the best answer is going to be C. Okay, so kind of I'd say this is one of the harder questions that was on the exam. Very conceptual, a lot of things to consider, but C is going to be your best answer. All right, guys, so I have the answer up there for number 4. Again, you're going to set up an ICE table. So this is the information that you have, 0.3 molarity of CH4, CO2, and then it tells you that you have 0.2 moles of CO at equilibrium. So our assumption is you don't start with any of the products, and so you're gaining product and losing reactants. Just make sure you take into account the stoichiometry, so it's plus 2x for the products and minus x for the reactants. And so these are the numbers you should get for equilibrium. Any questions on the ICE table itself? That part's pretty simple, right? All right. So from there, we need to set up our equilibrium constant expression. I guess the big or the common pitfall might be the exponents. Just keep in mind, since there's 2 in front of the products, you need to square both of the values on the numerator. And then from there, you simplify. I got about 0.026 and then repeating, which is pretty much 0.027. So that's going to be your equilibrium constant. Alright guys, let's go over this problem. Okay, so it tells you that you have this pretty much the system inside of a flask and it's allowed to come to equilibrium. And then, so basically this is at equilibrium, and what you're going to do is you're going to add O2. So you're adding O2 to disturb the equilibrium. And then you allow it to return to equilibrium. Okay, and then basically the question is asking, out of these four, which of the following has increased over its original equilibrium value? Okay, so the key thing to remember for this problem is, let's say there's a disturbance to equilibrium. Okay, so for example, let's just say that you have a certain amount, it applies for all three of them, but let's say you have a certain amount of NO2 at equilibrium. What happens is, if you decrease the amount or you change the system in some way, what's going to happen is it's going to go towards equilibrium, but one of the key points is that it never reaches back to the actual equilibrium value. Okay, so when you disturb the equilibrium and use the chandelier principle, the system is going to shift the disturbance back, but it never gets back to the actual original value of where it used to be. Okay, because it needs to maintain a ratio, right? And so it's not going to ever get to that to the original value. And so that's why, even though you go back to equilibrium, it's not going to be its actual original equilibrium where it was. It's going to have a different value, slightly deviated. Yeah, so I'm talking about NO2 here, but it depends on how you're changing it. So let's look at it for this one, okay? But that makes sense, right, guys? How it never goes back to the original quantity that it was at. So if you started at like 2 molarity and then you got rid of it, you dropped it to, like, let's say for example, like 1 molarity. It'll go up to hypothetically like 1.9 molarity, but it'll never get back to the full 2 molarity. So it never goes back to the original value. Okay? It's in your reading, by the way, which you guys all do on time. All right, so let's take a look at this. So the first one is asking, did the quantity of NO2 increase if you add O2? What do you guys think? If you add O2, where does the equilibrium shift? To the left. So if it's shifting to the left, will that increase the quantity of NO2? It does, because you're making more NO2 when you shift it to the left. So this is actually going to be the answer. But makes it a little bit easy.
The whole thing about the,
yeah.
Then why were you talking about how it never
it doesn't actually get to the original value because NO2 has increased. You have more NO2 than you did at equilibrium.
So doesn't it not really matter?
In this problem, no. But that's the premise behind why you can increase over its original equilibrium value. So you have more NO2 now than you used to have because you need to maintain a ratio because you added O2. So if you think about it in terms of your equilibrium constant expression, right? It's going to look like this. Okay, so this is the equilibrium constant expression. If you add O2, if you make this number bigger, what's the only way to retain the original ratio? Yeah, you need to make this one bigger as well. And so that's pretty much the point. And it'll get back to the same ratio, but the numbers here will be different now. And so that's kind of the point that I was trying to make with it. Okay. All right, so that's going to be your answer. And then quantity of NO will not be greater. Why will NO not be greater? Yeah, exactly. It's used to shift the equilibrium to the left. Okay, we know that if it goes back to equilibrium, the expression, the ratio is not going to change. Okay, so this is the ratio. The ratio is unchanged at equilibrium. And then, as we know, the rate does not change with when you disturb equilibrium. The rate stays the same. Okay. So those are the reasonings why those three answers will not be correct. B, it's because you use NO to shift left, so you'll actually have less NO than originally. The equilibrium constant K does not increase because the rate it describes the ratio of reactants and products at equilibrium, and the rate does not change because you're not affecting the rate at all. You're just affecting the concentrations at equilibrium. That's why A is the correct answer. All right, so if you guys take a look at number 6, it's basically asking you how are you going to increase the value of K, okay, in order to which change you need to make in order to increase the value of the equilibrium constant. So if you take a look at these, the equilibrium constant expression is going to look something like this. Now you can actually get rid of two of the answers pretty quickly. So if you guys think about K, right? K is a ratio between reactants and products, right? And so that ratio stays the same except when you change what? Okay, because if you disturb equilibrium, it goes back to the same K value. Yes, the K value is dependent on temperature. So if you guys want to make a note of that, the K value is temperature dependent. Okay, so you can have the same reaction, but if it's at a different temperature, it's going to be a different K value. So you can automatically cancel out B. You can automatically cancel out D. And D, it's a product. So if you add this, it's going to shift to the left, which you don't want anyway. So K is temperature dependent. And so your answer is going to be either A or C. Okay, make sense? Okay. So just remember that K is temperature dependent. All right, so we got to look at which side the energy wants to, whether it wants to be released or absorbed. So if you take a look at delta H, it is less than 0. So if it's less than 0, that means that it is a negative number. If delta H is negative, is energy a reactant or a product? It's going to be a product. So this is going to be your product. All right, so basically, if you want to increase the value of the equilibrium constant, what you want to do is you want to increase the numerator, okay? Which means that you want the equilibrium, or sorry, you want to add more product. Okay. And the way that you add more product is you increase temperature. And so it's going to be A. That's it. Okay, so I have 7 and 8 up there. I'll give you guys a brief explanation. Shouldn't be too bad. For 7, it's talking about how a change in volume will not affect the moles of a substance. Changing the volume is going to affect the pressure, right? And so you got to look at the gases here, just like the previous ones we've looked at. A, if you just look at the gases, it's 1 to 2. It's 3 to 2 for B. For C, it's 2 to 1. D is the one where you have 6 moles of gas and 6 moles of gas on the reactant and product side. I know there's other chemicals, but if you guys remember, liquids and aqueous doesn't really affect the pressure and the volume, right? And so you're only looking at the gases for D, and so D is going to be your best answer. Okay. And then for 8, solid, solid. So you only care about the gas, and you're looking for Kp, so you're going to look for pressures, and so pressure of CO2. So that's 7 and 8. Any questions on those? Okay. Let's go to number 9. This is the one I really wanted to do with you guys because this is the one where a lot of people got points taken off last year. So I want to make sure that you guys have some of the information. Okay. So for number 9, this is going to be an FRQ. It tells us in a saturated solution of silver 1 phosphate at this temperature, the concentration of Ag+ is going to be this value right here. And then it gives you the KSP, which is basically just the K value. Okay, now, before we go on, let's talk about that term saturated. Okay, you guys probably have heard this term, in just everyday life. We also talked about it in Unit 4, I think. But saturated just means it has the maximum amount of solute dissolved inside of it. Okay, so let's just say, for example, give you guys one of my beautiful drawings again. You have this solution. Let's say you're going to saturate it, which that means that you have the maximum amount of this compound dissolved inside of it. I don't know if you guys have done this because you guys might not be as weird as me, but have you guys ever tried to dump like a lot of sugar inside of water and like try to dissolve it? Okay, some of you, maybe I'm the crazy one too, but basically, when you try to dissolve something inside of water, when you add too much, what happens? It stops dissolving, right? It stays, it just starts settling on the bottom. Okay, that's when it's oversaturated. That's when you have the most. Saturated is when you have the maximum amount of solute dissolved in there. So if you want to write that down, so saturated just means you got the maximum amount of solute dissolved inside of your solution. Now, What that means is even if you add more to it, it's just going to settle on the bottom. And if it's settling on the bottom, what's the state of matter of it settling on the bottom? Solid. Okay, so just keep that in mind. Okay, and then when it's dissolved, this is aqueous. Okay, so that's what saturated means. So saturated is actually just a fancy way of saying the system is at equilibrium. Okay, saturation, in terms of this unit, it's basically telling you the system is at equilibrium. Okay, where you have the same rate dissolving and not dissolving. Yeah.
You say saturated, there's no salt on the bottom, it's oversaturated with salt.
So saturated can mean you could have stuff on the bottom. It's just you got the max amount already there. You'll see it in the upcoming parts. Okay, but just keep that in mind. Another way to think about saturated is the system is at equilibrium between solid and aqueous. Okay, I know we don't consider solids in the equilibrium expression, but just conceptually in real life, saturated means that you have an equilibrium between your solid and your aqueous phase. Okay, so just keep that in mind. It'll help with the later parts. All right, so with that being said, I'm going to give you guys, let me give you guys about 2 minutes. See if you guys can do part A. This is where you write the balanced equation for the dissolving of Ag3PO4 in water. Okay, so just the dissolving. Make sure you guys include state of matter notation, so whether it's a solid, liquid, aqueous, gas. And you're going to be using the equilibrium constant expression they give you here to do that. So let me give you guys about 2 minutes, and then we'll go over that together. If you guys finish that early, you can move on to the next parts. Alrighty, guys, so that's the answer for part B. I got 2.65, as long as you got something around there, times 10 to the negative 18. The reason why is because, first, you don't count your solid in your ice table. And since you're dissolving, right, so if you put something inside of water, you start with the solid, that starts to dissolve. So you start with 0 for your initial for your ions. You increase your ions. The coefficient is 3, so it's 3x and then x. You were given 5.3 times 10 to the negative 5, which is your equilibrium concentration for Ag+. So you just divide that by 3, and that'll give you PO4 3-. And then you just plug and chug into the equilibrium constant expression that they gave you. And from there, it's just math. Just be careful with your parentheses. All right, any questions on number 9, A and B so far? Hopefully that part's not too bad.
It's just possible because of products.
That's correct, yeah. So just think of it like...
Once that didn't apply though, like if they gave you a certain, is that only to give you the initial?
Yeah, they'll specify they give you initial amount, yeah.
They give you equilibrium equations.
That's correct, yeah. Yeah, and they're talking about dissolving, so if you think about it, if you put like, I think salt's the best example. You put a piece of salt inside of water, it starts at 0, right, the ions, and then eventually the ion concentration will go up. All right, let's move on to C. Okay, so C is the one that I think only one person got it last year, so that's why I wanted to go over number 9. So I want you to go through the same suffering that my class from last year went through. So I'm going to give you guys about 3-4 minutes. See if you guys can answer C on your own or with your partner. See if you can write your explanation. And then after that, I'll go over the answer. Well, you'll probably have to change your explanation. But let's have some fun trying to solve number C together, okay?
Why is Ag plus by itself the same molarity?
Oh, sorry, I wrote the wrong number. Thank you.
Oh, jeez.
Dude, I'm like copying this all down. Thank you, I appreciate that. 5.3 times 10 to the negative 5. My fault. I appreciate it. Yeah. Thanks. Alrighty, guys, let's go over C. So hopefully you guys got an answer. So before we start, let me just kind of go over what the problem is talking about. So it tells you that 1 liter of a saturated Ag3PO4 solution is allowed to evaporate to a final volume of 500 milliliters. So I have a beautiful drawing for you right here. You got 1 liter that's saturated, so it's at equilibrium. And we know that at equilibrium, the concentration of Ag plus is 5.3 times 10 to the negative 5. That's all at the top of the question. And then it's evaporating, and it goes to half of its initial volume. Everybody good? Okay. And then the question is asking, what is the concentration of Ag plus in the solution after it evaporates? Okay, so most people say that the concentration went down by half. Okay, and the reason why is because the volume went down by half. However, if you guys remember, saturated means the system is already at equilibrium, right? So if the system is at equilibrium at this concentration, even if you decrease the volume, the system is still going to go back to equilibrium, right? And so what that means is, let's just think about it in terms of the molarity formula, okay? So what we're doing here is we're dividing the liters by half, okay? But because it's at equilibrium, it actually needs to keep the molarity the exact same. So the answer is actually going to be 5.3 times 10 to the negative 5 molarity. I did lie to you. But you know what? It's not the first time and it won't be the last. Okay, so because the system stays at equilibrium, okay, it's going to have the same molarity for Ag+. So what's actually going to happen is the molarity is not going to decrease, because if you divide the liters by 2, what's going to happen is the Ag3PO4 that's aqueous is going to start to solidify at the bottom of the solution. And so that's pretty much what it is. So that's why it's important to know that saturated means equilibrium, because even if you decrease the volume, the concentration is going to stay the same. Yeah.
So basically it's just that like the ratio is staying the same because of that equilibrium.
Exactly. The ratio
That
stays the
number
same. Exactly. Yeah.
The right idea was.
Yes. Yeah. That's a tough one. It's really weird, because you would assume you decrease the volume, something's going to happen to the molarity, but since it's saturated, it's at equilibrium, the ratio stays the same. Okay? Easy way to think about it, again, if you had like 1 liter of salt water and half a liter of salt water, if they're saturated, the concentrations are going to be the same between them regardless of the volume. So that's pretty much it.